Hey, hey guys, this video I just want to talk a little bit about prime ideals. Okay, okay. Um, Obviously, well, prime ideals, this name, it comes from um, the like kind of trying to make a prime number into an ideal. So let's first just think about kind of a prime number and the ideal it generates. So let's think about where the name comes from. It just comes from um, the ideal P generated by a prime number in the integers, where P is prime. Okay, and then kind of some different things we know about this ideal. So one thing, okay, one thing we know is that Z mod P is a field. Another thing we know is that we could try and this is a capital P, meaning it like Z mod the ideal. Okay, another thing we know is like the definition of a prime number, which says that if P equals a B and A and B are natural numbers, then A equals 1 or B equals 1, and um, P is itself not 1. Okay. Right. So maybe meaning when I try and factorize P as two numbers, my factorization, one of the numbers has to be 1, and therefore the other number has to be P. Right. So it's kind of like a trivial factorization for a prime number. But in fact, there's another important like property that a prime number has, and that says that if P divides AB, then either P divides A or P divides B. Okay, all of these things are true. But this kind of like turns out to be the one that we use to define what a prime ideal is. Right, let's try and use this to define let's turn this into a condition on the ideal, this ideal capital P. You know, first of all, P is just the elements that look like P times N, where N is any integer. Okay, so let's try and rewrite all these conditions in terms of this ideal P. So P divides A, that just means that A equals P times, let's say, N1. P divides B, that means A equals P times N2. And P divides AB, that's the same thing as saying AB equals P times N3, right? In other words, P divides AB, that's like saying AB is an element of the ideal generated by P. So if we rewrite these conditions, what it really says is that if AB is an element of P, then either, well, P divides A, that means A is a multiple of P. In other words, A is an element of P. And similarly, or B is in P, right? So this is a condition we'll use to define what a prime ideal is. An ideal is prime is whenever you have a product that's in the ideal, one or the other, like, one of these two has to be in the ideal itself, right? So just to make sure it makes sense, we should check that, like, the ideal generated by 6 is not a prime ideal. Okay, but if we look at 6z, we have 2 and 2 times 3 is in 6z, but neither 2 nor 3, these are both not in 6z. Okay, so 6z, the multiples of 6 are not prime. That's good, because 6 is not a prime number. We want like a prime ideal to kind of generalize the idea of what a prime number is. Okay. And the real reason is just that it kind of works out in the end, but okay. So let's try it. There's kind of like a useful criterion for that tells you something about that relates when an ideal is prime, it relates that to the quotient. So let's talk about that. Maybe you've seen this before. Okay. All right. So let's just do a little proposition. Okay. Let R be a commutative ring. Oh yeah, before I do this proposition, I did write down what the definition for prime ideal was, but I didn't like officially call it a definition or anything. So let me just make it official and then write down the proposition. So let R be a ring. So for us that means commutative. And so on. And let I be an ideal. Okay. And also we'll in order, a prime ideal for us will be an ideal not equal to the entire ring. So under these conditions, then I is called a prime ideal if for all A, B, and R such that A, B is an element of the ideal, either A is in the ideal or B is in the ideal. Okay. And then our proposition is to describe this, describe when I is prime and describe it in terms of the quotient R mod I. So let's do our proposition now. Okay. Let R be a ring. I be an ideal. Okay. And I is not equal to the entire ring, right? Okay. And I is a prime ideal if and only if R mod I is an integral domain, meaning it is a ring where there are no zero divisors. And okay, let me just do a little aside here so you remember. No zero divisors. And in R, so R mod I is not the zero ring. And no zero divisors means that if A, B equals 0, then either A equals 0 or B equals 0. Okay. So let's prove this proposition. Okay. Let's suppose I is a prime ideal. Okay, so in this proof, whenever I put a bar on anything, that's going to be the corresponding element of R mod I. So to note for A and R, A bar is just going to be the coset of A. Okay. And now let's suppose I is a prime ideal. And under our hypothesis, well, the definition of a prime ideal says that I is not equal to R. Okay. I guess according to my definitions for integral domain and prime ideal, I could have omitted this hypothesis, but I guess I just felt safer to put it. Sorry about that. But anyways, okay, so what we really need to show is that R mod I has no zero divisors. So let's suppose that I take two elements in R mod I and I multiply them together to get 0. So let's suppose that A bar times B bar equals 0 in R mod I. Okay. Well, in terms of arithmetic in R mod I, this means that if we look at AB, AB is 0 mod I, so it means that A times B is in I. Okay. Because like A bar times B bar is just AB, all bar, and AB bar is 0 if AB is an element of I. Okay, now I is prime, so A is in I, or B is in I. Well, that just means if A is in I, that just means that A bar equals 0. If B is in I, that just means B bar is equal to 0. Thus showing that R mod I has no zero divisors. Conversely, I mean, to show that if R mod I is an integral, if R mod I is an integral domain, you can show I is a prime ideal just by kind of reversing things, which I will just briefly do. So now suppose R mod I is an integral domain. Then suppose A times B is in I. Well, then AB bar is equal to 0, but AB bar is just A bar times B bar. Now, in my integral domain R mod I have A bar times B bar equals 0, so A bar equals 0, or B bar equals 0. So if A bar equals 0, A is an element of I. If B bar equals 0, B is an element of I. As required, showing that I is a prime ideal. Okay. And some examples of prime ideals. Let me just give you, of course we saw like every prime number generates a prime ideal of the integers. More examples of prime ideals. Right. You have in R, which might be like ZX, you might have the ideal P, which might be like the ideal generated by, let's say, what's a good one? X squared plus X plus 1. That might be one. Okay. What's another example? 2. In R equals Z, we have all the prime ideals, all the ideals generated by prime numbers, and then we also have the ideal generated by 0. Well, that's because the Z itself is an integral domain. So Z mod 0 is just going to be isomorphic to Z, which is an integral domain. So 0, that tells you that 0 is prime. Okay, so that's another example. What's another example? Let's think about it. I guess in R equals the coefficients of like the polynomials with real coefficients, you can have P to be the ideal generated by X squared plus 1. Okay. Or let's do one more. Let's think about, we can just think about this if you want. In R, which is going to be like maybe the complex numbers, the polynomials with complex coefficients, but in like 2 variables. And then like what's a prime ideal? P might be like, here I can write down like an irreducible polynomial. Something like that. Okay. This turns out to be, all of these are prime ideals in their respective rings. Okay. And what we saw from the proposition is that to prove that these things are all prime ideals, you can work and take the ring and mod out by each of these ideals and prove that you have an integral domain. Okay, so that is enough for this video. Let's do a similar discussion in the next video, except for maximal ideals instead of prime ideals. And we'll see that prime ideals, when you quotient out by them, you get an integral domain. For maximal ideals, when you take the quotient, you get a field. Okay.